Alrighty, on to chapter 5, exponential and logarithmic functions. We'll start with a brief section on composite functions or compositions of functions. Basically, what a composition of functions is you put one function inside another one, the result being called a composite function. Specifically, given two functions, f and g, the composite function denoted f composed with g, so a little circle there is read as such, f composed with g, is defined by the equation f composed with g is the function acting on x that gives the output of f of g of x. So we're really putting the g function inside the f function. We're composing the two functions. The domain of the composite, f composed with g, is a set of all numbers x in the domain of g, such that g of x is in the domain of f. So algebraically, at this stage, we would have domains where we avoid square roots of negatives and division by 0. That's going to get a little bit more complicated when we make it to logarithmic functions later in this chapter. We can't take logs of zeros and we can't take the logarithm of a negative number if we stick to the use of real numbers, which is what we'll do for the remainder of the course. But to make some sense out of this domain comment, it's really the little blobs in what's this kind of grayish region. Here we have, get a little bigger, a composition of f and g. Notice when we compose f with g, g comes first. It's almost as if we read from right to left. The g function comes first, and then the f function acts on that. So first we'll have the g function. Here is, schematically, the domain of g. So g will take the elements of the domain and map them over here. This left blob in the center is the range of g. So it takes the domain, maps it to the range. The domain of f is the good values we can plug into function f. For example, values where we won't get square roots of negatives or division by 0. And these may not mesh entirely, but we need part of the range of g to be a subset of the domain of f. And then the f function will take this output, g of x, and map it to something in the range of the composition. So what we have schematically really is the things in gray to concentrate on. Here's the domain of the composition, f composed with g. Here's an element x. The g function takes that element x over here into a g of x value, and then the function f takes that g of x value and maps it over here to an f of g of x value. Now for us, all these domains and range things are subsets of the set of real numbers. So it's not as exotic as this illustration may imply. And we may have outputs from function g, that is elements of the range of g, that are not in the domain of f, that are not legitimate inputs for function f. For example, g might output a negative number, and the f function might be the square root function. Well, we can't take square roots of negatives. So that would be such an example as is given in this particular x value. But we're taking x by g to g of x, and then f takes that to f of g of x. More directly, the composition f composed with g, that composite function, takes this value x and maps it over here to this value in the range of f composed with g, to this f of g of x value. So we're putting one function inside another. If I may be informal about it, and that's how I describe it next. And this is a conversation we would always have shortly before talking about inverse functions. And inverse functions are addressed. I think it's in the next section. So continuing this idea of a function as a machine, a composite function can be thought of as feeding the output of the first function into the second function. We take x as the input. The first function is g. That outputs a g of x. G of x is in the input for the second function, f, yielding f of g of x. As I call it, the inside function g, we're putting g inside f. It's the one that comes first. As given in the diagram above, first there's g, and then there's f of g of x. In terms of the little machine diagram, we take x, we put it into the g machine, it outputs a g of x value. That g of x value then becomes, assuming it's in the domain of the f function, then becomes input in the f function machine. And then the output is f of the input, f of g of x. The output here is g of the input. Input was x, output is g of x. For this function, the input is g of x, so the output is f of that input. That is f of g of x. So there it is schematically. Given on the previous slide. Here it is in terms of this machine idea of a function as a machine. And we'll just illustrate this with a bunch of examples. Okay, so some examples on compositions of functions from section 5.1. First, given graphs of functions, evaluate compositions. Evaluate each expression using the graphs of y equals f of x and y equals g of x is given. Find first g composed with f of 1. All right, this is interchange. We had f of g, f composed with g in the setup, but we're just interchanging the roles of f and g to deal with this in the opposite order. They want g of f of 1 and 5 and f of g of 0 and 2. So we'll go through all 4 of those. They're all very similar. First, g composed with f of 1 by definition is g of f of 1. So we need f of 1. Here's the f function. What happens when you plug 1 into the f function? Here's the x value 1. When we plug that in, we get out a y value of -1. The point 1, -1, the point 1, -1 is on a graph of function f. So when you plug 1 into the function f, you get -1 out. So that's what f of 1 is. So g of f of 1 is actually g of -1, substituting for f of 1 in its value, -1. How are you going to find g of -1? Go to the graph. Here's the g function. Here's x equals -1. When we plug that into the g function, looks like we get out 3. The point -1, 3 is on the graph of the g function. So g of -1 is 3. And therefore, the composition g composed with f of 1 is g of f of 1 by definition. F of 1 is -1, that's g of -1. And we just saw g of -1 is 3 from the graph. So it's simply a matter of reading numbers off of graphs. With the composition, you take the output of the inner function and plug that in as input in the outer function. The first function outputted -1, and then we took that -1 and we plugged that into the outer function. The outer function, the g function, g of f of 1. And the other 3 will be quite similar. Part B, they want g composed with f of 5. Okay, same idea. F of 5, we need that. We need f of 5. X equals 5 is here. Here's the point on the graph of y equals f of x. The point 5, 1 has an input value, x coordinate of 5, output value, y coordinate of 1. So f of 5 is 1 because the point 5, 1 appears on the graph of the curve. We want g of f of 5. Well, if you want g of f of 5, that's g of 1 because f of 5 equals 1. So now we'll go to the curve g and concentrate on the x value 1. Here's 1. There's the point on y equals g of x, the 0.1 comma 4. The 0.1 comma 4 tells you g of 1 equals 4, g of the x value equals the y value. So the composition, g composed with f of 5, that is g of f of 5, is f of 5 is 1, that's g of 1. We just saw g of 1 is 4, and so the output is 4. We take the output from the first function, the f function, in this case, the first one encountering the variable. Take the output from the f function, which is 1, and input it in the outer function, the second function, the g function, and that produces the 4. Let's do it again, but in the opposite order. How about f composed with g of 0, f of g of 0? 0, g function, looks like it outputs 5. They didn't label the point, but it looks like the point 0, 5 is on the graph of the g function. So g of 0 is 5. Substitute that in. We then have f of g of 0, we have f of 5. I'll take the output from that function, make it input in the f function. So here's the 5. We go up this time to the f function. We want f of 5, 5 comma 1 on the f function. Tells you f of 5 is 1, f of 5 is 1, and so that's the value of the composition. F composed with g of 0 is f of g of 0. G of 0 we saw was 5 right here, and we just saw that f of 5 is 1 by looking at the graph. So that's the answer to this one. Let's do the final one. It also is an f composed with g. Question, f composed with g of 2. That is f of g of 2. Okay, here's 2. The g function will output 2. If the g function outputs 2, we'll take that output of 2, plug it into the f function, and that results in an output of -2. And the answer is -2. Just speeding it up a little bit, but all the details are here in terms of we're using points on graphs to find function values. Sometimes it's the f function, sometimes it's a g function. It depends. I personally don't dig this notation so much. This is a cleaner notation. It tells you precisely when you're dealing with which function. In this case, the value 2 first goes into the g function, and whatever comes out of that goes into the f function, out of one machine and into the other in terms of what we had in the section. I guess we're just running through a list of problems here. Let's look at another one. Okay, given two functions, f and g, do the same type thing. So this time they've given us formulas instead of giving us graphs. But they're formulas in terms of the variable x. F of x is x to the 3/2. G of x is 2 divided by x plus 1. And they want you to find these various compositions. First one, part A. F composed with g of 4. Second one, g composed with f of 2. Well, I tell you what, let's find f composed with g and g composed with f. And we'll have those functions sitting there, and we can apply those functions directly to the 4 and the 2. F of g of x, f composed with g, would be, well, let's replace g of x with its formula. G of x is 2 over x plus 1. So we're taking f of something. What does f do to the something? Takes that something and raises it to the 3/2 power, right? It's the x is the something, but the input is whatever x, the output is the whatever to the 3/2 power. Here the input is this thing here. Well, then it takes this thing here and raises it to the 3/2 power. So we get 2 over x plus 1 to the 3/2 power. There's the composition of f composed with g. If we did it the other way around, which we need for part B, we'd have g composed with f. What's f of x? F of x is x to the 3/2. So we'll replace f of x with x to the 3/2. What does g do to things? It takes that thing, adds 1 to it, and makes it a denominator with 2 in the numerator. It gives us 2 divided by thing plus 1. The thing here is x to the 3/2. So we get 2 divided by x to the 3/2 thing plus 1. And of course, these two are different. So the order matters. If we take f of g of x versus g of f of x, that shouldn't be surprising considering how involved f and g can be. All right, so part A wants f composed with g of 4. Well, we could go through it having an input of one function and the output becomes the input of the other function. Or since we've stated what these functions are, here's f composed with g, we could simply take this and plug in 4. So take the variable x, replace it with 4. Always put parentheses around those so you can see the substitution that's been made. This gives us 2 divided by 5 to the 3/2 power. That's an ugly irrational number. I'll just leave it as 2/5 to the 3/2. Part B, g of f of 2. Well, we've got g of f of x. It's this function here. So we'll simply take this function here and plug in 2, giving us 2 divided by 2 to the 3/2 plus 1. 2 to the 3/2 is some irrational number. We could modify the form of this, but we're always going to be stuck with the irrational number. There's square roots of 2's in this somewhere or other. So we'll just leave the answer in that form. One could rationalize the denominator if one were so possessed, but I'm happy to leave the answer like that. Not much is to be learned beyond this value, and I certainly don't want to numerically approximate it with some calculator. Part C wants f of 1. F of 1, well, we'll take 1 and plug it into the f function. That would give us 1 to the 3/2. There's your 1 to the 3/2. 1 to the 3/2 is just 1. So we're going to plug that into the f function. The output from the previous will give us 1 to the 3/2. That's still 1. So evaluate f at this number and then take that output and evaluate f at that output value. A little trickier because the output and the input were both 1s, but that's because we're dealing with a power of x function. Part D wants g of 0. Okay, this one's a little more interesting. G composed with g, evaluated at 0, g of 0. So we'll evaluate g of 0. Go up to the g function, plug 0 in for x. That'll give us 2 over 0 plus 1. 2 divided by 0 plus 1. That's just 2. And that goes into the g function. Well, the g function takes that input and gives us 2 divided by input plus 1. The input this time is 2, giving us 2/3. So there's how we can symbolically compose functions and then plug numbers into them. I like this better. In calculus, you'll be doing things where you take compositions of functions. Later in here, we'll be composing functions with a special agenda in mind. We're looking for inverse functions as our future agenda in this chapter. Number 30, state the domain of the composite functions, f composed with g and g composed with f, where f of x is 1 divided by x plus 3, and g of x is -2 divided by x. Okay. These are a little trickier. We're going to do some simplifying, and when we simplify, we'll have to be very careful. We'll compose the functions. Let's take f composed with g. F composed with g, that would be f of g of x. G of x is -2 over x. So we get f of -2 over x. By the way, notice x can't be 0. That'd give division by 0. What does f do to something? Takes 1 divided by the something plus 3. So f of this is 1 divided by this plus 3. Simply replacing x with the input, as you always do with functions. We can leave it at that, or how about we simplify it a little bit? This is a compound fraction. It's a fraction in a fraction. So we'll multiply by x over x. Ooh, x can't be 0, right? That gave us division by 0. So keep that in mind. I still know x can't be 0 because I've still got division by 0. If we distribute here, we get x in the numerator, If we distribute here, being very careful, we get negative 2x over x times x, or if you like, negative 2 times x over x. Distribute plus 3x. Okay. X can't be 0, right? Right. That information is contained right there because we got an x in the denominator. Division by 0 potentially. But x divided by x, that's just 1 unless x equals 0. So we're going to replace this with 1 and get x over negative 2 plus 3x. Do you see anything here that says x can't be 0? Actually, if we plugged in x equals 0, the numerator would be 0, not a problem, and the denominator would be negative 2, not a problem. But x can't be 0. That was part of the story at the beginning. By canceling, we've seen this several times at this stage, by canceling these x's from here to here, we've lost the information that x can't be 0. It's explicitly stated here that x can't be 0 because we've got division by x and we can't divide by 0. That's not explicitly stated here. I can plug 0 in for x here. Well, then this part and these are different functions. This one's not defined at 0 and this one is. To make them equal, then we need to make sure this is not defined at 0. And we do that by having to actually manually write in this is valid provided x is not equal to 0. So x not equal to 0, 0 is not in the domain of this composition. If you like, leave it right here and you'll see it explicitly. This is cleaner, but requires this disclaimer that x is not 0. All right, so we got a problem when we have division by 0 or square roots of negatives. There's no square roots here, so that ain't an issue, but there's division by 0. Negative 2 plus 3x. That quantity could also be 0. If that's 0, then x is what? 2/3. If x equals 2/3, this will give us 0 in the denominator, so we can't have x equals 2/3. We can't have x equals 2/3 because that results in division by 0. We can't have x equals 0 either because ultimately that results in division by 0. Remember, g is not defined at x equals 0. So neither of those two numbers are good numbers. That's the only thing we're concerned with is division by 0. There's no square roots in this one. That's the only thing that could go wrong. And it goes wrong for these two values and no others. So the domain of the composite function f composed with g is all real numbers except for 0 and except for 2/3. So we use the little open parentheses to remove the point 0 and the little open parentheses to remove the point 2/3, as we've done previously. They also wanted the domain of g composed with f. Okay, then we'll start with that function. G composed with f, g of f of x, that is. F of x is this thing here, 1 over x plus 3. So we'll take g of that. What does g do to something? Takes negative 2 divided by the something. So g applied to this gives us negative 2 divided by this, the quotient 1 divided by x plus 3. Also a compound fraction. Let's do the same little deal of getting rid of the compound fraction. Let's multiply by x plus 3 over x plus 3. After all, that equals 1 unless x equals negative 3. Hey, x can't be negative 3 or we'd have division by negative 3. So we'll multiply by x plus 3 over x plus 3. Numerator becomes negative 2 times x plus 3. Denominator, multiply the 1 by the x plus 3 to get x plus 3 divided by x plus 3. X can't be negative 3. You can see that. That would give division by 0 here, for example. Let's cancel these and simplify. Put it in lowest terms, but in so doing, we produce negative 2x minus 6. Negative 2x minus 6 all by itself, that is not equal to this function because that negative 2x plus 6, that is defined at negative 3. You can plug negative 3 into this part, nothing goes wrong. Plug negative 3 into this, you get division by 0. So this negative 2x plus 6 all by itself that doesn't equal that previous function. They're equal everywhere except for at -3. So we got to write that part down, as always. So we get equality provided x is not -3. The only thing that could go wrong is division by 0. And at x equals -3, that division by 0, it's out there. I see it right here, division by 0, division by 0, division by 0, division by 0. I see it explicitly until we cancel those x plus 3's. And now I don't see it anymore. It still has to apply if these are equal. And that's why we have to write out explicitly x is not -3. So that takes care of the division by 0. There's no square roots to worry about, square roots and negatives again. And so this is defined for all real numbers except for -3. So we'll take -infinity to infinity and use the little parentheses to remove -3. And there's the domain of that composite function. Let's do one with square roots. So more stuff can go wrong. Now we got square roots and negatives. Looks like division's not an issue because there's no division in either of these functions. But state the domain of the composite functions, f composed with g and g composed with f, for f of x is x squared plus 4, and g of x is the square root of x minus 2. F composed with g, that is f of g of x. G of x is the square root of x minus 2. So I skipped a little step there. F of g of x, here's g of x. What does f do to things? F takes input, squares the input and adds 4. The input is the square root of x minus 2, so that gets squared. 4 is added. X minus 2 square root of squared, that's simply x minus 2. But remember, from here, we can't take square roots and negatives, so this comes with a constraint that x is greater than or equal to 2. We can't take square roots and negatives. The square root disappeared. That information still is only valid when x is greater than or equal to 2. This alone, x minus 2 plus 4, that doesn't equal this when x is 0, for example. If I plug 0 in for x here, we get -2 plus 4, 4 minus 2, we get 2 out when x is 0. If I plug 0 into this, we get the square root of -2, and we can't deal with the square root of -2. So we're stuck. These are not equal, and that's why, again, we have to put a disclaimer in there. More involved disclaimer than a single point this time, because now we're dealing with square roots and negatives. So only valid when x is greater than or equal to 2, when we're taking square roots of non-negative things. -2 plus 4 is +2, so this reduces to x plus 2, and it still comes with a disclaimer that x is greater than or equal to 2. We can only take square roots of non-negative numbers, unless you let me use complex numbers, and that's not what we're doing at this stage. So the domain is all real numbers greater than or equal to 2, and interval notation, that's the interval including the 2 with a square bracket to infinity. How about the composition in the other direction? We compose g with f, g of f of x. F of x is x squared plus 4. So we've got that. What does g do to input? It subtracts 2 from the input and takes a square root. So we'll have the square root of input x squared plus 4. And there's the subtracting 2. Simply replaced x here with the input. The input is x squared plus 4. That's x squared plus 2, square root of. We need to make sure we're only taking square roots of non-negative things. Hey, x squared plus 2 is always non-negative. It's always greater than or equal to 0. It's actually always greater than or equal to 2, which means it's also greater than or equal to 0. We don't have a problem with square roots and negatives for any of these. So this time the domain is all real numbers. We don't get square roots and negatives in this particular function. In this particular function, we had the constraint x greater than or equal to 2, because when we dealt with x less than 2, somewhere in there was square roots and negatives. I don't see it here. I see it here, though, and that's why we had to write this out. So compose in a different order, get dramatically different domains in this case. Show f composed with g of x equals g composed with f of x equals x itself when we take f of x to be 4 minus 3x, and we take g of x to be 4 minus x divided by 3. The idea here is where we're going with this in the next section, is that whatever one function does, the other function undoes. If I take this composition and I put 7 in, assuming 7's in the domain, we'll get 7 out. G will take that 7 and turn it into something else. F will take that something else and turn it back into 7. Similarly, if we look at the composition in this order, whatever one function does, the other one undoes. That's the reason we're getting out a function that does nothing. It's the identity function. We put x in, we get x out, assuming it's in the domain. Okay, well, they give us the function, so all we have to do is take the composition, f composed with g of x, that would be f of g of x. Here's g of x, 4 minus x divided by 3, f of that. F takes an input and outputs 4 minus 3 times the input, so we'll get 4 minus 3 times the input, 4 minus x divided by 3. The 3's will cancel, leaving us with 4 minus the quantity, 4 minus x, be careful with the parentheses, 4 minus 4 is 0, negative x is a positive x, indeed the output is simply x. As claimed, call this a proof, it's really a computation, but we're proving something arguably. How about the composition in the other direction? Right, they said show it in both directions. Okay, we did the f composed with g. Now for the g composed with f of x. That is g of f of x. F of x is 4 minus 3x, so that's g of 4 minus 3x. What does g do to an input? 4 minus the input divided by 3. So we'll have 4 minus the input divided by 3. That's 4 minus 4 distributing the negative, plus 3x divided by 3. 4 minus 4 is 0. That leaves us with 3x over 3. 3's cancel, leaves us with x as claimed. We were supposed to get x out in both cases. Whatever one function does, the other one undoes. So that together, when composed, they're the function that does nothing. You put any number in the domain, and you get that number out. Okay, this deals with compositions as well, but in a slightly different way. Find functions f and g so that f composed with g of x equals this function, 1 plus x squared cubed. Okay, here you very much want to think of that output function, that h of x function as they call it. You want to think of it as an inner function and an outer function. What do you see as the outermost operation? I see some stuff cubed. That's kind of on the outside. What gets cubed? Well, the inner stuff is 1 plus x squared. So thinking of this as an outer function and an inner function, and that's what you get with compositions. I think the outer function would be the cubing function, and the inner function would be the 1 plus x squared function. Here we're looking at f composed with g of x. That means g is the inner function and f is the outer function. So I think we'll take this as g of x and the cubing function as the f function. That was a little imprecise. Let's make sure we got it right. By computing f composed with g of x, with these as our candidate f and g functions. And for this reason, thinking in terms of inner and outer functions. F composed with g of x, what's g of x? We think it's 1 plus x squared. So we'll take 1 plus x squared, f of that. F takes input and cubes it. So it'll take that input of 1 plus x squared and cube it. And that's exactly what we were aiming for. It worked as desired. So we'll take f of x as x cubed and g of x is 1 plus x squared. So there's how we can use compositions of functions to go through and take a given function and rewrite it as a composition. This will be an important task in Calculus 1 when you do something called differentiation. You will differentiate compositions of functions, and you have to recognize what this is as a composition of functions. Okay, one final example from this section says the volume V in cubic meters of a hot air balloon of radius r in meters is given by V of r equals 4/3 pi r cubed. That's a volume of a sphere of radius r. If the radius r as a function of time t in seconds is r of t equals 2/3 t cubed, where t is greater than or equal to 0, then find the volume V as a function of time. Okay. It's a composition of functions for the following reasons. We've got volume as a function of r, and we've got r as a function of time, and we want volume as a function of time. So we want to eliminate r and express volume not in terms of r, but in terms of time. It's a composition. V is a function of r, V of r, as it says explicitly there. R is a function of t, time, as it says explicitly there, r of t. So to get V as a function of t, we'll take the composition. V composed with r of t, that is V of r of t. We know V, we know r, we're good to go. V of r of t we had as 2/3 t cubed. So here's a 2/3 t cubed. V of an input, here the variable is r, takes that input, 4/3 pi input cubed. So we'll have 4/3 pi this thing cubed, 4/3 pi, 2/3 t cubed, quantity cubed, putting the input in parentheses as I always do. And that I guess we can simplify a little bit. We'd have 2 cubed, 3 cubed, and t cubed cubed, right? Taking care of the cubed stuff. 2 cubed is 8, 3 cubed is 27. T cubed cubed is t to the 9th. Multiply exponents under those conditions. And if we multiply numerators and so forth and denominators out, that gives us 32/81 pi t to the 9th power. Okay, so volume is a function of time is exactly that. It was just a composition of functions question. You're changing from variables of r to variables of t. Also something you will do in calculus, probably in connection with something called related rates. You'll have a composition of functions. You'll ultimately be interested in how things change with respect to time. The question here might come down to you is, at some particular time, how fast is the volume of the balloon changing with respect to time? So there's some examples involving compositions of functions. What we'll do in the next section is focus more on that type of example where we had functions composing to give the identity function. F composed with G and G composed with F were both the identity function. You put X in, you get X out. That'll lead us to a conversation about inverse functions, and that we need to deal with log and exponential functions. It turns out log and exponential functions are inverses of each other. You'll also see the inverse function ideas in Precalculus 2 when you deal with a trig function and the inverse of a trig function. So I'll see you in section 5.2 next, and we'll start looking at inverse functions. Have a nice day.